All right, so hi everyone. I'm very excited to be here. Thank you so much for having me. I'm Zagorac, and I'm currently a postdoctoral fellow at the Perimeter Institute for Theoretical Physics in Waterloo. And if you don't know what a postdoctoral fellow or researcher or scientist or whatever noun they put after it is, it basically means they give you a PhD, but they didn't want to give you a professorship yet, so you have to do some stuff in between. So this is the stuff in between. Okay, so my talk is on what we can't see in the universe and why it might be fuzzy. And I just want to shout out Quentin Weyrich from the DDO, who made this, I think, really, really awesome visual for this talk. So as a little preview, because we love to give previews in academia, we're going to start with what we actually can see in the universe, what we do see in the universe, things like small things and big things and wiggly things, and we'll get into what each of those mean. And then we'll talk about the things that we don't see in the universe, which are question mark size things. And finally, why it might be fuzzy. And another way to voice that is, what if some of the biggest things in the universe were made up of some of the smallest things in the universe? So we'll get to that. So this is, a room full of astronomers and astronomy enthusiasts. So let's start with what we can see in the universe, because, we love using little things like this to see things in the universe. So there's a bunch of big things that we can see in the universe that might not look big in the night sky, but we know that they are big if we could sort of like approach them and see them and touch them and stuff like that. So in a sky like this, you might see things like planets and stars in our own galaxy and newly formed stars and nebulae and clouds of gas and galaxies from billions and billions of years ago with some new telescopes like this one, right? So this is JWST, which is sort of the astronomy community's pride and joy, mostly because it took approximately the age of the universe to get it launched and funded. I'm just happy that it launched relatively early in my career, because I was really starting to think that it might have a 2030 launch date. But anyway, this thing is really cool for a variety of reasons and some very clever engineering that I absolutely cannot explain to you because I chose the wrong college major for that. But you can see things such as these sort of like baby stars forming here, which is really cool. And you can see these galaxies that are approximately 13 billion years old, which is pretty wild when you think about the fact that our universe is not even 14 billion years old. So you can see some really, really awesome stuff. And with recent, very clever telescopes like this, what we can see is our own black hole at the center of our own galaxy. So this is the Event Horizon Telescope, which is a bunch of telescopes that already exist that came together to basically form one mega telescope the size of the Earth and take pictures like this, where what we see here is a bunch of gas being sort of thrown around very wildly around the central black hole, which is the center of our galaxy, which is incredibly cool. So this is the first time that we can kind of see a black hole. What we're really seeing is the gas around a black hole, but nevertheless, I find it quite excellent. Other ways of looking at things that come from the universe, so we can see a bunch of small things coming from the universe. So for instance, what I'm illustrating here is, so this is the Ice Cube Neutrino Observatory that is located in the South Pole. So, it gets approximately as cold as Canadian winter. And so what you can see with instruments like these are a bunch of little particles that we know exist. So things like electrons and neutrons and protons and muons and neutrinos and so much more. So the way that works for this particular machine is that people drilled very deeply into the Antarctic ice these kilometer-long tubes, and they put something on it called photomultiplier tubes, which basically says that if you get a really small signal of just a little bit of light, what they'll do is they'll multiply that light, so you're able to see that really small signal way better. So what we see here is a super energetic particle that is passing through, interacting with something in the ice, and then leaving a trail. And these things might be coming from our galaxy, they might be coming from outside of our galaxy. It's this whole question of what cosmic rays are, which are these energetic particles that are buzzing around space. And they're really, really common, but they interact really infrequently, and this is one of the ways that you can see them. And I just think it's really nuts that somebody spent all of this time, digging through literally kilometers of Antarctic ice so we can see this. So that's pretty cool. There's a lot of pretty cool experiments out there, right? I should have tested this. Let's see if it works. But the other thing that as of recently being 2015, or really it was announced in 2016, but we saw it in 2015, the thing that we can see is gravitational waves. And so gravitational waves are a really, really different way to think about seeing the universe, because we don't really see them. We sort of like feel them, or at least we have instruments that are able to feel them. And what they are these little wobbles in space-time that are so, so small that you need like incredibly precise instruments to see them. And you need incredibly violent events to happen in the universe to cause them to be strong enough such that our super precise instruments can see them. So one way, or like the canonical thing to think about here, is two black holes colliding. And as they are colliding, they're so heavy that they're bending space-time around them. And when they collide, they sort of send those wiggles out into the universe and we can see them. And there's this really, really cool sonification project, which is basically you take the signal of this, yes, it worked. So you take the signal from something like this and you can move it around and put it basically, interpret it as a sound wave, right? And so you can hear the two black holes colliding. So let's hear that again. It doesn't sound as impressive as it is, but I think it's really, really cool. So you can see these sort of basically two black holes that are sort of orbiting around each other, and they get closer and closer. What we say is they in-spiral. The spiral that they form gets smaller and smaller, and eventually they collide. And so this is the chirp heard around the world that you just heard. So this is the whoop. And that's really, really awesome, because that's a totally different window into our universe that we now have that has nothing to do with light, right? You don't need a telescope to know this. And so what's really exciting is when an event, you can see both the gravitational waves from it and also light from it. That's called multi-messenger astronomy. And that's this like whole new window into the universe, we like to say, that we've opened. So there's a lot of cool things in the universe. There's a lot of cool things that we can see or hear or feel in the universe, right? There's a lot of these things that we have access to. Which begs the question, what are the things that we can't see in the universe, even in principle? Not because the next telescope hasn't launched, or not because, we'll be able to in 5 years when the next gravitational wave detector is launched, but even in principle, we can't see them. And so it turns out that actually we can see quite a lot of the universe. So if you think about the whole universe, if you're a cosmologist like me, that means you think about sort of where the universe came from and how it evolves in in a holistic sense. And so you can think about what's called the energy density in the universe. So all of the stuff in the universe, what is it made out of? And it turns out 70% of it is made out of dark energy, and 30% of it is made out of what we call matter. And that matter is about 80% dark matter, and it's only 20% luminous matter. And luminous matter is things like stars or galaxies and dust, or you or me or this table, or really anything that you've ever really felt yourself interacting with. So everything we know is this 20% of this 30%. So that's something like 4 or 5% of the universe. The things that we don't know then are dark matter and dark energy. So somewhere along the line, somebody decided that we are going to call the things that we don't know and that we can't see dark. And so dark matter was called dark matter, dark because it doesn't really interact with light, right? We have no way of directly seeing it. And matter because it behaves like, tables or you and me or stars, in the sense that it gravitates, it has some mass. But that's all really that we know about it. My understanding of why dark energy was named what it was, it's dark because we don't know what it is and it doesn't interact with light. And it's called energy so that Americans can ask the Department of Energy for funding when they're researching dark energy. That's the best story I've ever gotten about it, and I'm sticking to it. So actually quite a lot of the universe, this is a XKCD comic because I love XKCD comics and I think they describe the state of the field pretty well, actually. But yeah, so there's this whole lot of dark matter around and we have no idea what it is. And so this is what I do. This is sort of what I research. This is what they pay me the extremely mediocre bucks for. And so if we can't see dark matter, how do we even know it's there is a really excellent question to ask. So thank you for asking it. So what we can do is we can look at galaxies that we can see. We can see all the stars and the dust and the gas and stuff that emits light in the galaxies, right? And so you can construct what's known as a profile. So in this case, a velocity profile. So the question is, how do things move going from the center of the galaxy and going out? And so if we just count up all of the stars and the gas and all of the stuff that we see, we expect it to make this line. So we expect it to look something like this. But actually what we're seeing is something like this. And so there's a huge gap in here, right? There's all of this missing mass. There's extra mass that we don't know where it's coming from. So said another way, if you look at all of the stars and the shiny things, you can take just how shiny they are and convert them into an expectation of a mass, like how much mass of stuff should be in this galaxy. And that's one number. The other number is if you look at how a galaxy moves, it moves because it gravitates, and that allows you to calculate its mass. That's the second number. And the second number is like 5 to 6 times bigger than the first number. So this gap is really the question that we are trying to answer. So this is one of the ways that dark matter was initially posited. People like Vera Rubin were really instrumental in this. Nowadays, we have more and more evidence that dark matter exists. So we're not fully hanging our hats just on this, but this is sort of the canonical early days example of what we know about it. Okay, so let's say I've convinced you that there is some missing mass in the universe that doesn't interact with light, but it does interact with gravity, right? It has mass. And we call that mass dark matter for whatever reason. So where does this dark matter live? Where do I go in the universe to find it? And so this is like a galaxy. This is obviously an artist tradition of a galaxy. If this is our galaxy, we live about here. And so this is all of the, again, luminous matter of the galaxy. And this around it is what's called a dark matter halo. So this is regular matter, which cosmologists sometimes call baryons because we find it deeply uninteresting. And this is dark matter. So it lives inside of a halo of dark matter. Basically, it's all this extra mass that is surrounding the galaxy and also inside of it. And the next question is, okay, so you have this halo of dark matter, but what is the halo made up of? Like, what kind of, is it a particle? What is it? Where does it come from? And so that's a really excellent question. It's worth approximately 10 million Swedish krona, which is what the current going rate is for the Nobel Prize. You may have to split it with like 2 or 3 people, but still. And so there are a ton of ideas out there. One of my favorite memories from going to a conference really early on in my doctorate was, it was a conference on dark matter. And the person who was organizing it, whose name I unfortunately don't remember, stood up in front of everybody and said, like, yeah, we've been working on this dark matter thing for like, a few decades now, and we've really like narrowed it down to like 94 orders of magnitude, which is a lot. So there's a ton of explanations that you can have. You can have all of these sort of like weird particle explanations. You can have all these weird particle explanations, some more weird, some less weird if you're a physicist. Maybe all of them equally weird if you're not. But also we can have like really high mass stuff, like 10 to the 30 kilograms or something. So explanations for dark matter have come out like, oh, what if dark matter is a bunch of black holes that we forgot to count up, right? Because black holes have mass and they're dark. We don't see them, we see the stuff around them, right? And so people are researching a ton of these different ideas. And the type of idea that I will be telling you about today is called an axion, and it lives all the way here on the left because they're these super, super tiny particles. The elephant in the room, of course, is a very different explanation of dark matter, which is to say dark matter doesn't exist. There's no extra particles. What's wrong is our understanding of gravity. What's wrong is that, you and me, we all live on Earth, right? We have experience with physics, but we only have experience with a certain regime of physics. Like, you can sit on a plane and go at, I'm going to embarrass myself, I don't know how fast planes go, let's say 700 kilometers per hour or something like that, right? But you're never going to be traveling like close to the speed of light. And so we have experience with physics. We have a lot of experience and instincts about physics that are good, but they're really confined to Earth. They're really terrestrial instincts. And so if we lived somewhere at the very edge of a galaxy, maybe our instincts would tell us that, hey, gravity works differently here, which is a really lovely idea. And we fundamentally don't really understand gravity, and there is something to understanding more about it. But unfortunately, the modified gravity idea of dark matter just doesn't really exist. Or it exists, but it doesn't really work. People have tried to make it work. There's still very active research about it. If one day I have to eat my words because we figure out that gravity is in fact modified, I'll be very happy because there will be a very interesting universe that we live in. But thus far, there's not really evidence to that effect. So right, dark matter, what is it? It's confusing. And so because I'm here to sell you something, I'm here to sell you on the idea that it could be fuzzy. And we'll talk about what that means in a moment. So fuzzy dark matter is one of these ideas of dark matter that I brought up, and it's made up of particles that are called axions. The story is that when these were sort of first proposed for completely unrelated reasons, actually, in the previous century, they were called axions because Axion was a brand of dish soap, and axions are really convenient because they like clean away your mistakes. Like they clean a lot of problems in physics. If you've never seen Axion and dish soap like I haven't, it's not that fun. The alternative name was the Higlet, like the little Higgs, which I think was way funnier because it also sounds like piglet, and so you could have Winnie the Pooh characters, but unfortunately they weren't that forward thinking. But in any case, so these particles, for better or for worse, are called axions, and they're super, super tiny. And when I say that they are tiny, so comparing a axion, the ones that I studied by mass, to an electron, right, one of the smallest particles that we know of, is akin to comparing an electron to a tennis ball. So it's incredibly, incredibly small, which is one important thing that it is. The other thing is that it's a boson. It doesn't really matter what that means physically, other than these are particles that like to cluster. There are generally two types of particles called fermions and bosons, which some of you may know about. But so fermions like to be sort of in pairs and very individualistic. They can't all be in the same state, but bosons just like to cuddle. So a lot of bosons can live really, really close together. And this is really important for the galactic profiles that I was telling you about earlier. So looking at how galaxies spin and looking at what their profile looks like is one of the first ways that we realize, like, there's a lot of mass here that we're not saying what gives. And so these days, it's also one of the ways that we really test our theories against data to say, does this make any sense? Is this a good explanation? Is it verified by the data? And so here I'm showing you two different types of profiles. One is called a chord profile because it has this sort of core. And the other one is called a cuspy profile because this thing is called a cusp. And the reason they're important is because these cuspy profiles come out of a dark matter candidate called cold dark matter, which is not so much an explanation of dark matter. It's not like one single particle that we understand where it comes from and how it would evolve. It's like the most minimal set of assumptions that you can make about dark matter and put into like your computer simulation and then run them forward and get something that kind of looks like the universe back. And so for a long time, it's been this problem that these types of halos make this cusp here, which is not very physical because if you can tell at small distances, so at the center of the halo, it kind of goes to infinity, and we don't like that. Infinities aren't very physical. We want something to be finite. We want it to have a value. It can be a big value, it can be a small value, but it has to be like a well-defined value. Fuzzy dark matter, on the other hand, behaves basically the same on the outskirts. So this is why this is sometimes called a skirt as well. But in the center, it has this core, which is also sometimes called a soliton. And the reason it does this because all of these particles like to huddle in here, right? They're bosons. And so they make this core instead of arranging themselves in this cusp. So that's sort of what the profile of a fuzzy dark matter halo looks like. But what does the actual halo look like? So if the universe were fair, it would look like a very fluffy, cute black cat. But actually what it looks like is something like this. So this is a simulation that I ran for one of my papers that I wrote. And what you see here are two blobs of dark matter colliding. And after they collide, what they form is something that looks like what a dark matter halo might look like. And so there are really two things that I want you to notice here about fuzzy dark matter that make it different than just the generic cold dark matter. So the first thing is this central blob. So this is the core that I was telling you about that is also sometimes called soliton. And the reason this exists is because of its very, very small mass. Because the particles have really, really small mass, they're super tiny, quantum effects come into play. And so there's something called the Heisenberg uncertainty principle in quantum mechanics that says that basically you smear out a particle along, you can't really be sure of where it is on some length, and that length is inversely proportional to the mass. So the smaller the mass is, the farther that length is where you don't really know what's happening. And for these things, because they're so tiny, remember they're smaller than an electron in the same way that the electron is smaller than a tennis ball. The size of that smear is about a kiloparsec, which is about the inner region of a galaxy. So these are sort of like galaxy-sized quasi-quantum systems. which makes them really, really interesting to me. And that's why they formed this core. The other thing to notice here on the sides is all of these wiggles. So this is basically the turbulent nature of fuzzy dark matter. So the lighter it is, the higher the density is in this area. The darker it is, the less dense the area. So there are these sort of low density regions in addition to these sort of like denser regions, right? And this is also a quantum effect. It basically comes from quantum superposition. And so that's really, really cool and interesting because it allows people like me to use some lessons we learned from quantum mechanics, which we used to study like really small things like atoms, to the biggest things in the universe, like dark matter halos. So, right, I've gotten a little bit ahead of myself because I love this stuff. So the question is, how is a fuzzy dark matter halo like a hydrogen atom? Why can I use this quantum, right? So if you take quantum mechanics at some point in your life, or listen to a course or read a book about it or something like that, or really if you're really into chemistry and you learn a lot about chemistry, you might learn about these things called orbitals. So a hydrogen atom is like a hydrogen nucleus orbited by one electron, right? And so we really want to think about it as just sort of like the Earth and the sun, right? The Earth goes around the sun and we always know where it is. But atoms aren't like that. What they do is they form these orbitals that look something like this, which is basically an area where it's more probable that we'll find the electron at any given point if we were able to measure exactly where it is. But again, it's sort of smeared out. It's not a deterministic process. And you can do actually the same thing with fuzzy dark matter halos. So again, this is from one of my papers. And so you can take this halo and say that, oh, okay, so because all of these particles are so small that I can use quantum techniques, let me calculate what's known as its eigenstates, which are the same as these orbitals, right? And see where the particles like to live. What are those shapes? And are those shapes that I can see in astronomical data somewhere? So in fact, you might see that these are similar. So there's this what's called a ground state, which is like very spherical, right? This is just like concentric circles or something. There's this dipole, which is sort of these two lobes that you have together. And this is a quadrupole when you have 4 of these lobes together. So it really looks like a really big hydrogen atom in some sense. And so you might say, okay, that's cool, but how does that come into play when I'm trying to like compare with astrophysical data? And so one way that I've used this is to basically form halos like I showed you before by merging these blobs, but merging different numbers of blobs in different orders. And the reason for this is because in cosmology, we have reason to believe that how these dark matter halos are made and their galaxies are made really, really matters. Their merger history is what's called is important because some of these things sort of like grow from the early universe around denser parts of the universe, but a lot of them will just merge with each other. They will fly by each other. They will hit each other and go through each other. It's a really violent process to be a growing dark matter halo or a growing galaxy. Like galaxies fight while they grow. And so this is one of the ways that we were trying to connect that process to this sort of quantum-like behavior. So if I can make these halos in different ways, and I know exactly what their orbitals look like, I can ask it, hey, how much of the halo is in this ground state? And the reason I care about this ground state is because that's exactly the core that I was telling you about, right? That's why it looks nicer in the central part, that generic cold dark matter halo. And that is the thing that I want to get at because I have observational reason to believe that galaxies have cores rather than disks. And so if I take several halos that I formed here, what's on the x-axis here is time, so we're just looking forward in time. And what's on the y-axis here is how much of the density of the entire halo is in that ground state, is in that core. What is the size of that core? What is the relative mass of that core to the rest of the halo? That is something I want to know. The numbers here just indicate how many blobs I've merged. Basically, the more blobs I merge, the more massive the halo is because they're all the same mass. And so if we follow one of these lines, so let's follow the darkest line, basically what I'm asking my code is, okay, is there a core at the center? And it says, nope, nope, nope. And then it says, oh, I changed my mind. Yes, there is. Because this is the moment that those two blobs have merged. And this is the moment that I've made a halo and a halo has a core. And so this core contributes around 60% to the total mass of the halo. Sure, it oscillates up and down a little bit, but if you kind of squint, this is almost a straight line, right? So it looks like the relative size of the core isn't really changing that much. And that's really interesting to me because this has been a big question in my field. A big question in my field is, okay, halos have cores, but if I have a Milky Way halo, right, if I'm looking at our halo, at our galaxy, how big of a core do I expect? Versus if I'm looking at some like little dwarf galaxy, right? And so using this sort of like weird quantum language, I was able to comment on this because I know exactly what a core is. It is that ground eigenstate, right? And so thanks to the very small particles and the quantum mechanical idea, I can tie that to the very large, enormous effects of the dark matter halo. So this is really doing science across really, really big scales. And the answer is sort of here. So what is on the x-axis here is just some parameter that basically tells you the energy and the mass of the halo. Don't worry about it too much, but those are sort of the two scales of the halo that we're worried about, right? And what is on the y-axis is the relative mass of the core. So the mass of the core divided by the mass of the total halo. So these are things like percentages, right? And so the reason I plot this quantity is because there has been a lot of previous work in the field that's showing, that tried to answer this question. In fact, it was so important that there were like 3 or 4 different answers to the questions, all predicting a different type of scaling. So a few of them predicted something that looks like 1/4. Or 1/3. So here, these two lines predict 1/3, but this line doesn't. And the reason is that is the line where I allowed my halos to have that merger history that I mentioned before. So they didn't just instantaneously form and then just like chill there, you know, unperturbed by anything else for billions of years. What they did is form violently by interacting with other halos. And so when you do that, the relative size of your core changes. So if I'm looking around the cosmos and I'm trying to put limits on like, oh, is this a reasonable dark matter candidate? Is this a reasonable theory that I can apply to the real world? Just looking at the size of the core and saying, is that the size of the core that I expect for the halo is not enough. What I really have to worry about is how that halo got there, right? It's a little bit more complicated than that. So as a quick recap, we started with the things that we see in the universe. These are things like small particles, big galaxies, or anything really galactic scale, and also things like gravitational waves that we don't see, but are now sort of opening what astronomers call a new window into our universe. What we don't see in the universe are things like dark matter and dark energy. I only talked about dark matter today, but there are plenty of people doing really important work on dark energy because it really is most of the budget of the universe. And finally, I introduced fuzzy dark matter and talked about why it might be fuzzy. So sort of one application of how you can take these really, really small particles and the theory that governs really small particles like quantum mechanics and use those lessons to sort of apply them to really big things in the universe, like dark matter halos. So yeah, thanks for your attention, and I'll take any questions.